So good morning to everyone and welcome to this last lecture of the Doctoral School 2020. My name is Antonia Larese and I'm going to speak about MPM. First of all, let me thanks again the organizers of this school, Professor Wu and Professor Pastor, for inviting me. I mean, it was an honor of being one of the lecturer of this school, and I hope you will enjoy this presentation. Unfortunately, I need also to apologize because it won't be an amazing presentation as the presentation you've seen yesterday about MPM. I mean, the work done at the PFL is really amazing. Now we are going back to fundamentals and to the basics. So be patient. I hope you enjoy it in any case. The merit of this work is the merit of my students. So I would like to thank Ilaria. Ilaria Iaconeta is a former PhD student. She got her degree last December. She was a student of mine when I was in UPC, not in UPM, in Barcelona, and I was working in CIMNE. CIMNE is the International Center for Numerical Methods in Engineering. I've been there for 13 years before coming back to my home university in Padua, where I got a position a couple of years ago. And we always had a very strong collaboration with Technical University of Munich. In fact, this work is a joint work between CIMNE, UniPD, Padua, and TUM. And as I was saying, Ilaria was a fellow of an ITN project on granular materials. Seen from the industrial point of view, it was team up project. And I mean, her PhD was the opportunity for us to try this new method. I mean, you will see in a few minutes why I ended up working in MPM. I hope it will be clear. And she arrived at the correct moment, and we started together developing this implicit version of MPM. And her work was then followed by Bodhinanda Chandra, who was a master student at that time from TUM, who came to CIMNE first and to the University of Padua after, to work with me some months on coupled problems. We started speaking of coupled problems with Nanda and of boundary conditions, which will be the topic of the second part of the talk. And finally, last but not least, Veronica, who is now a PhD candidate at TUM, and she's also working. She's really taking the lead of the group of the work of Ilaria and Nanda. So the presentation is structured as follow. I will follow quite a lot the lecture notes. I will first of all motivate why I ended up using MPM and why I wanted to try this new experience, and then I will try to explain to you the first steps we have done in this new world. We are new babies, so with the you won't see amazing videos, but basic formulations. And I will end up, I will spend also some words about formulations. So irreducible MPM versus mixed formulation to overcome problems, locking problems, basically volumetric locking problems that appears when you deals with incompressible materials. And the last part of the presentation, I will present the work we are doing on coupling MPM with other techniques, basically FEM. Why I'm working on MPM? Well, my work is to simulate the effects of natural disaster, of water-related natural disasters on structures. Buildings, dams, roads, piles of a bridge, dikes. It depends. And of course, it's not only flooding what I'm simulating, but it might be mud flow or other type of fluidized soil impacting on a structure. So there are basically two questions that I need to answer. This is a long-term research, of course, it's not, it's a wide topic. I would like to understand which is the effect of flow events, of extreme flow events on existing structures, you have to think that our structures, not only in Italy, but at least all around Europe, have been mostly built after the Second World War. So we are really speaking of many years ago. And if we are looking at the prediction of due to of frequency and intensity of extreme event in the future, unfortunately frequency is increasing and intensity as well. So I mean, it is highly probable that our design, the design criteria used 50 years ago are not really suitable for the boundary conditions, for the forcings that our structures are subjected to now. And that's a problem. That's a problem also because we need to change our design criteria when designing new structures, but we need to design retrofitting measures also on our existing structure. I don't want to mention all recent disasters, not only in Italy, but also in Italy, due to this lack of analysis. When I say flow, the impact of flows, of course, I'm speaking of different kind of flows, not only flats. I'm dealing with mud flows. I'm dealing with flows of mud or water impacting on earth structures. So the interaction between different kind of soil, water, and eventually structures. Or I'm also considering the possibility of simulating big objects flowing within the flow. What do I mean with that? Well, actually, I'm dealing with a lot of different frameworks and techniques depending on what I need to do. Well, I'm analyzing, I've worked a lot on non-Newtonian rheological models. So as you know, it was mentioned by Professor Wu in the first day, if you want to analyze granular materials, flows of granular materials, you can either treat them as fluids, or you can start from a structural mechanics, solid mechanics formulation, and try to simulate the flowing, the large deformation of this material. Of course, you need to reach a common point, which is somehow in the middle, because you are dealing with a material which is not even a solid, not even a solid material, not even a fluid material. So that's the reason why I worked a lot in CFD formulation for non-Newtonian materials, especially that family of non-Newtonian material which has, yield thresholds, which are the Bingham plastics, the viscoplastic material like Bingham plastic or Herschel Buckley. I know that Professor Pastor is much more experienced than me on that topic. And more recently, I switched on the opposite side. So I started analyzing the large deformation of mud, of soil, of mass movement, starting from a soil dynamic formulation. This was also one of the reasons why I switched to MPM. Then, of course, multiphysics in this kind of events is somehow necessary. So you need to deal with fluid structure interaction problems, with soil structure interaction problems. It depends. I'm not even talking about the multi-phase nature of the soil itself, because as you understand, this is important, of course, but the main topic is the impact of violent movements on existing structure. So the dynamics, the triggering of the phenomena is not really the object of this research. And when we deal with this, as I call it, multi-components model, we are speaking of multiphysics. We are speaking of the need of different techniques, because as you will see, I will stress this concept through all my presentation. I'm not really fighting for one single technique. There is no single technique for all the events you want to simulate. I guess it depends. We need to go for multi-physics for sure. We need to be ready to switch from FEM to particle techniques to either discrete elements. It depends. It depends on the needs and on the necessity you have in that time. And then one part of my research is also on what is called embedded or immersed boundary methods. So on unfitted techniques that allows you to simulate big objects carried on by the flow. So the interaction between immersed object in a flow, basically. Of course, I added here them. I've never worked with them, but it's also one possible technique that you could consider if you have trees or cars carrying on by the water and you need to simulate them, but you're not interested on the deformation of these objects itself, while embedded methods or immersed methods are more oriented to the analysis of the interaction between the two objects. So this is somehow the framework in which I move right now, but today we will concentrate basically on large deformation models and a glimpse of couple models itself. So why I ended up to MPM, because I wanted to simulate large mass movements and their impact on structure. We can find example all around the world of this phenomena, unfortunately, also because the consequences are not only from the economic point of view, but also from the human point of view, really impacting. So the first steps I moved in this world were to develop CFD codes, because of course when you start speaking of natural disaster, flow-related natural disaster, you're speaking of floods, you're speaking of, in my case, the topic of my PhD was overtopping in embankment dams. So I was worried of extreme floods extreme events that cause the raise of the upstream level of a reservoir until overtopping, until reaching overtopping, to reach the top of the dam. And the initial analysis, my initial steps in the research were in finite elements. Actually, it was a strange form of finite elements, but I will not enter this topic now. And free surface flows. When you use Eulerian descriptions, so you're using a fixed mesh approach, you need to somehow track the evolution of the free surface. Also, yesterday in the second talk, you saw level set was already mentioned. In fact, I used level set to track the evolution of the free surface in the transition, in the free surface flow and in the seepage itself. Level set is basically a technique to track the evolution of the free surface, because the free surface is considered a surface of zero distance, and then you use on your domain the definition of a distance field, which is a smooth enough field that you can convect according to the fluid velocity that you have already calculated. And using the convection of this free surface solved together with the Navier-Stokes equation for the fluids, you reach the movement of, you can follow the movement of the surface. It's not as simple as I have just explained, but I mean, the concept behind it are this one. And one peculiarity was that I was dealing with rock fill material. So the seepage, as you see here in this layer or in these brown layers here, is really highly permeable. We extended this work recently to considering also the presence of air and considering the possibility of parallelizing also this code in MPI to obtain high performances, basically. This is a recent work of another master student who continued with my free surface code in Barcelona, Simon Venkowski, who was also a student in TUM. And of course, here we are already going towards high performance computing. So as you see, my background is in finite elements. But already during my PhD, I had the need to go and to simulate large deformations in materials. And that was why I decided to use at that time the particle finite element method. It was mentioned, that this technique was mentioned in the first lecture by Professor Bui. Uh, well, this technique was originally ideated by Professor Sergio Idelson in SIMNE and Professor Ognata as well, for simulating breaking waves. We are going back 15 years, more than 15 years ago. And I have to say that when I arrived to SIMNE as a master student as well, um, I was asked to validate these techniques for CFD problems. And yeah, it was a long time ago. So I started working with particle methods, but I mean, calling particle methods is a little bit misleading, because what's PFEM? It's finite elements. It's Lagrangian finite elements. So you are meshing at every time steps your material domain. You're solving your equation in a Lagrangian kinematic framework. And at every time steps, of course, since the mesh is highly deformed, especially in CFD, less, of course, in structural mechanics, what you need to do is to erase completely the mesh, to keep the cloud of nodes, and then to reconstruct the mesh. Of course, to reconstruct the mesh, you need to triangulate all the domain, and then to find a technique that allows you to say which of these elements should be kept for the simulation of the next time step and which of these elements should be removed. This technique is the alpha shape method, which is a geometrically based technique that basically design the circle circumscribed to each of these triangles, and decided which is the maximum radius which is admissible. If the radius is too big, or the diameter, I mean, it's the same. If the diameter of this circumscribed circle to each element is too big, is bigger than a fixed parameter, then the element is removed. Otherwise, it is kept. Of course, you understand that depending on the alpha shape parameter you decide, you can obtain either this mesh for the next step calculation or this mesh here. And you might see already one of the defects of these methods. I mean, conservation of mass is not really maintained. It highly depends on how you choose this alpha shape parameter. Nevertheless, I mean, this is a very flexible technique. It's really very powerful also. I mean, it's FEM. It's FEM in a Lagrangian way. We did a lot of works or using PFEM. This was the analysis of the impact of a hypothetic landslide in a reservoir in the north part of Spain. We were asked by the water authority, well, the owners of this dam here, which is located in the north part of Spain, to analyze. They measured some movements, some strange movements on this slope, and they asked us to simulate the presence of this big mass of landslide falling into the reservoir, to see if the waves generated by this falling would have affected the dam. Or we were asked, well, many years ago, there was an accident in an harbor in Spain. Well, they were building up this harbor. They constrained a sort of, they built a boundary using these concrete caissons, which, I don't know if you're able to see, they were 18 meters high. It means that it's a sixth floor building. Each of these blocks was a sixth floor building, just to make you understand. They just construct the boundary of this area, and then they take sand from the sea, and they throw it here to fill in all the area, which is now full of containers, so it's completely finished. But there was a big accident in New Year's Eve, possibly due to the to the liquefaction of the mud here inside. And basically, as you see in this simulation, these caissons were really pushed far in the sea. Uh, so we were asked to simulate this, and that's not easy. I mean, you have mud here, you have water here, you have rigid bodies interactions, because these are not deformable, but they can move. So it's multi-body also interaction. And I mean, we were able to do it more than 10 years ago. Unfortunately, PFM need remeshing, and today it might be a bottleneck. At least we are not able to do remeshing in parallel, and this is still a major drawbacks. And alpha shape, as you saw before, might also be another drawbacks. It's not really, I mean, you're not maintaining, conservation is not really one of the strong points of this method. Although, for example, the work done by at the Polytechnic of Milan by Professor Cremonesi or by Professor Alessandro Franci, by Professor Agnato, of course, it's really going through all these drawbacks and making step forward. For my point of view, I worked in PFM, but mainly in CFD. So when I needed to have a more, when I needed to think of something for soil mechanics, I needed a structural mechanics formulation, a solid mechanic formulation, and I mean, it was a complete change of paradigm. Also, there are people working in soil mechanics using PFM, but not so many. While in MPM, there is a strong literature of geomechanics people. Uh, Actually, there was also PFM evolved in the direction of PFM2. Professor Sergio Idelson and Pablo Becker in the Mumolade project, which was, I mean, the PI of this project was Professor Wei Wu. They developed these techniques, which was PFM2, that used a background grid and let's say trackers, points that are tracers of the evolution of state variables, which is somehow a similar concept of what MPM does. This evolution of PFM towards PFM2 is somehow a step forward towards MPM. The points, as I said, are tracers. They are not material points, but the idea is pretty much the same. So considering, let's resume what I was looking for. You know the context now, and you know why I left the PFM. I wanted some technique in the continuum mechanic frameworks. Indeed, I was not looking for discrete elements or any other sort of discrete technique. And I want the technique to be able to handle large displacements and deformation problems, so geometrically nonlinear problems, and handle Lisser-dependent materials. So I also wanted the material nonlinearity to be considered. And of course, if possible, I want to improve conservation properties, and I wanted the technique to be parallelizable. The natural choice was MPM then, and that's the reason why I ended up working in this new framework. What's MPM? Let's go back to the idea. Actually, I see it as an enriched version of FEM. This is due to my background. I know I'm biased by my background, but I see in MPM the possibility of giving something more to FEM. I don't see MPM as something completely different. Why I say that, I try to explain it in a couple of slides. So let's imagine to have a problem domain, this big square here, where we have two bodies, a square and a star. A square is subjected to some sort of rotational velocity. The stars is subjected to a vertical velocity, and there are some forces around. Nothing, I mean, just this is the material you're analyzing. You have basically two ways of treating it using FEM, either using an Eulerian description or a Lagrangian description. In the case of the Eulerian description, you have a fixed mesh that covers all the all the problem domain, okay? All the domain of the problem. And you need some sort of techniques that tells you where the material is and that allows you to follow the boundary of the materials that you're analyzing, either because this boundary can or cannot have nodes on the boundary itself. It's the case of the star. You don't have nodes on the side of this star, on the edge of this star. And how can you apply boundary conditions there? If you have volumetric forces, everything is okay. But if you don't, you need some sort of tracking technique, like level set, for example, to track it. On the other hand, if you simulate these two objects using a Lagrangian kinematic framework, well, you have the nodes that are real material nodes. So they move with the materials and they follow the materials. And you don't have nodes outside the materials. Where you don't have material, you don't have nodes. You just fix usually a bounding box. So to decide all the area in which you want to analyze the movement of this body, and out of this area you are not analyzing anything. So if on the case of the Eulerian FEM, you have the advantage that you don't have mesh distortion because you don't move the mesh, you have several drawbacks or difficulties. I mean, I'm a level set developer, so I really appreciate the use of Eulerian FEM, but I need to say that imposing boundary condition is quite complicated and it might be diffusive. You need to pay a lot of attention what you're doing, and you are solving equations that are a little bit more complicated in the sense that you have the convective or advective term. And you know that this term is a source of instability, especially if convection dominates over diffusion, for example. In the case of Lagrangian FEM, on the contrary, also the imposition of boundary condition and the tracking of the boundary is something which is more natural, so you can do it quite easily. But you have mass distortion. So either you do like in PFEM and you remesh, or you cannot calculate, of course. What does a MPM do in this case? Well, a little bit of both things. It tries to merge the advantages of one and the other. Let's say the advantage of the Eulerian description is that mesh is not moving. And in MPM, mesh is not moving. Let's say during the whole process, mesh is not moving. But we will see that inside each time step, it will. In fact, each time step will be a Lagrangian time step. But let's start from the beginning. We have a background fixed grid, and we have the material domain, which is discretized with a set of material points. The material points are crucial in MPM since they carry the history of the process. Every information is stored inside the MPM, inside the material points, while nothing is stored from one step to the other in the grid. So we basically perform a FEM updated Lagrangian step. So we are solving the equation in a Lagrangian kinematic description of motion. We allow the mesh to deform within the time step, but we perform everything like it's a Lagrangian finite element step. With the only difference, well, let's see it afterwards. For the moment, everything is like FEM. But at the end, we keep the position of the material points in the new position, and we recover the original position of the mesh. Every information is stored inside the red dots that are the material points, and nothing is stored inside the mesh. So at the next time step, we are going back to this picture here, but with this new configuration, all the information is stored in these red dots that are the material points and will be projected, mapped onto the background mesh to perform again another updated Lagrangian step. So what I was saying is that there is one difference, which is not a minor difference, since it's a mathematical problem, let's say. at the beginning of our simulation, we can decide where to put the material points because it's the developer or the code developer or we are those who decide where to put the material points at the first step. But then it is the process that make the material points to move. Of course, the governing equation, but also all the calculation. That means that since these red dots are nothing but the integration point of our finite element grid, at the beginning of the simulation, we can decide that the position of these finite elements integration points is optimal. That is, it's on the Gauss point. But after the first step is gone, you cannot decide it anymore. So the position of the integration point in our calculation is arbitrary. This is the only main difference. While I say that it's a main difference, I mean, it's one of the cause, well, from the mathematical point of view, this is absolutely not optimal. And this also induce some problems in convergence, in nonlinear problems and dynamic problems. Then there is a second word in my title, which was important, that is implicit. Most of MPM code are explicit, especially in geomechanics. Anura 3D is explicit, and all the, I mean, except the group of Durham University, Professor Kume, most of the people are doing explicit code. Gilkey and Weiss are those who developed something very similar to what we did. In the implicit version, Cummins and Beckbill, they propose a Newton-Krylov approach for the simulation, for the use of implicit MPM. But propose a formulation using high order elements in this case, or not linear elements. And Sanchez also proposed something else for quasi-static problems, so very limited applications. And as I said before, Professor Coombs Eugard from Durham University are pushing a lot implicit, as we are as well. Why implicit and not explicit? I mean, it's easier to do it explicit. Let's go back to the original notion of implicit and explicit formulation. Just, of course, we are speaking of time integration, okay? And usually the derivative with respect to time, so the primary variable, so the derivatives, the velocity with respect to time, is, or of displacement with respect to time, is an ordinary differential problem. And you can approximate this derivative using the velocity, for example, the velocity at the previous time step, un, and at the next time step, unknown, un plus 1, where delta t is the time interval of the time length of the step itself. And this is equal to our f of u, where u can be either un or un plus 1. This is a mistake. It should be here in the subindex. This makes a big difference because in the case of explicit formulations, you have the unknown at times un plus 1 only in function of everything known at the previous time step. Conceptually much easier. You don't have to solve any systems. You can just calculate your unknown using previous information. Or more accurate but more complicated, you can calculate your unknown considering that also your function is expressed in un plus 1, so at the next time steps. That means that you need to solve an equation system to obtain your un plus 1. It is indeed more difficult and expensive solving a system that evaluating, that calculating only the variable, but it is more accurate. And you have a scheme that where stability does not depend on the wave propagation speed in the media. And especially this is more favorable when you have very low velocity, load rate, or quasi-static problems. Of course, if you have impulsive problems, go for explicit, but this is not really the case in geomechanics usually, and it's also more robust. Then we have to be honest. We are, as I said before, for me, MPM is an FEM. So I was coming from implicit formulation, and it's a natural way to go. What's MPM? Let's go to the fundamentals of MPM. You have already seen it in the previous talk. Well, we have a background grid. As I said, is a square. These gray squares are the nodes of our grid, of our finite element mesh. And these dots, either gray or blue, are the material points, which are the integration points of our grid. And I will indicate the capital letters I will indicate the nodes with capital letters, while the material points with non-capital one. We can use either linear, triangular, quadrilateral, and therefore tetrahedral or hexahedral elements in 3D. It's more or less similar. There are formulations for both kind of elements usually. Of course, as always, as in FEM, triangular meshes allows you to treat unstructured grids, and therefore more complicated geometry. You can define non-regular boundaries, while quadrilateral meshes are more rigid in this sense. And as I said before, we decide to use as initial position the Gauss point of the finite element background grid. So at least at the beginning, mass transfer is performed with minimal error. One small detail. If you identify, since all the assembly procedure and all the system creation is done as in FEM, we need to point out that every material point, every element in our material point, in our MPM code, is made by the material point itself plus its connectivity, so plus the connectivity of the finite element in which it falls into. So we have element I, which is material point Pi with its connectivity ijk, and material points J, it's the material point Pj plus its connectivity, because it's important that at each time step we know in which elements the material points fall into. Otherwise, we are not able to map information between the mesh and the material point itself. Just nomenclature very, very quickly. When I use the the upper script n, or n+1 is the time in this index. I've already spoken of the subindex, and then I also indicates the iteration on the left of the variable. And I use displacement, u as displacement, u dot as velocity, and u double dot as acceleration. So which are the MPM stages? First of all, we have an initialization phase in which basically we map all the information on the finite element mesh. Then we have a FEM step, an updated Lagrangian FEM step. And finally, we need to recover the position of the grid and to store all the information on our material points. So let's go a little bit more in detail. What's the initialization phase? Well, we have a cloud of material points with all the information stored inside. We have a background grid which does not know anything, and we need to extrapolate the information from the material points to the node, and then to predict the fields of velocity, acceleration, displacement on the nodes to perform using a Newman scheme. So what we can do at every time step, since every material point has its own mass, using the information of the previous time step, we can always evaluate the force on each material point and the linear momentum in each material point. And using that quantities, we can interpolate, we can project these quantities on the background nodes. So we can evaluate the mass arriving to each node of the elements in which each material point is falling into. We can evaluate the linear momentum and the forces at time n. And of course, once we have this information on our background grid, we can also evaluate an expected a prediction of the velocity and the acceleration on each node of our mesh using the linear momentum and the forces. So we start knowing displacement, velocity, and acceleration on the particle, and we have an extrapolation of velocity, displacement, and acceleration also on the nodes. We can then predict the new velocity, displacement, and acceleration using a Newmark scheme, and eventually we will correct it if we do not reach convergence. But then we are done in the sense that now we can do finite elements. We can do a finite element step from Tn to Tn plus 1. We solve an algebraic system of equations. How do we do it? Well, we calculate for each element the local left-hand side and right-hand side in the current configuration. We assemble all the information, and then we solve the system iteratively. Of course, during the calculation, since it's in Lagrangian fashion, we can deform the mesh, and the material points do not change their position within the elements until the solution reaches convergence. What we are solving is a system of equation of the classical type, so stiffness matrix, unknown, and residual of the momentum equation, of the governing equation, basically. We use it, since it's a nonlinear problem, we will see it when we will speak about formulation, but we need to linearize our nonlinear problems using Newton-Raphson schemes, basically. I'm not entering the detail of how this case built, since, as I said before, we will analyze the formulation in very brief. After we have the elemental system and we have done the assembling, we can solve the system iteratively and evaluate the new displacement. Displacement in this case is the only unknown. So we can check convergence. If we didn't reach convergence, then we perform a Newmark correction. We take the previous value at iteration key, and we add the new value of the delta displacements. So we can evaluate also the new value of the velocity and of the acceleration. And then we redo all the cycle until we reach convergence, and we go to the next step. Once we have reached convergence, what we need to do is to transfer nodal information, to interpolate back nodal information onto the material points. Okay, so we have here the arrows are not well posed. This should be pointed to node I, J, and K, and interpolating information from the nodes to the material points. Okay, once this is done, the position of the material point is updated to the new position. So this point was here, PI was here, and it's now moved to the new position, the blue point of PI. Once this is done, we can just delete all the movements, all the information that we have in the mesh, and recover back the undeformed finite element grid. And we, of course, need to check in which elements the new material points, so the new position of the material points, falls into. This K material points here was before in these elements, and now it's in element IJK, while these yellow points here was before in element IJK, and it's now outside element IJK. Okay, so these are additional things that usually we're not doing in finite elements, but are needed in MPM. Okay, so some words on formulations before going into to see the examples. Usually when you speak of finite elements, you are solving the strong form of your problems, where you have the momentum equation and the mass conservation equation in their strong form. You have a set of boundary conditions, the Neumann boundary condition and Dirichlet boundary condition on the variable or on its gradient, basically. And what you do, you obtain the weak form of these equations. How? Well, multiplying all the terms of this equation by a weight and integrating over all the domain. Then, using Green's lemma and other passages, you basically slow down the order of continuity required to your functions and to your weight, and then you achieve usually a Galerkin formulation for your problem. In this case, the classical way of doing it is considering one single unknown. Displacement is the only unknown you are considering. And then the rest of variables like strain, stress, and whatever is evaluated starting from the definition of the unknown itself. It's not sufficient to reach the weak Galerkin form of the problem, since this is still a continuous form and this is still a nonlinear form. As I said before, we are unfortunately dealing with very complex problems which are highly nonlinear. So what we need to do is to linearize this problem, and this is classically done using Newton-Raphson procedures or similar approaches. So you have your residual in the last unknown configuration and the directional derivatives. I know that most of you know better than me all this stuff, but it's just for coherence. We are just going through them. Then you obtain a discretized form, just substituting your continuous unknown with your finite elements unknown. So you evaluate it on your nodes, UH basically, and you obtain your algebraic system that can be seen as K du equal to the residual. Inside your K, which is the stiffness matrix, you have both the static and the dynamic contribution, and the static contribution itself can be divided into the geometrical part, the geometrical stiffness and the material stiffness matrix. Okay, we are using linear shape function. We are not using high order elements. So the shape function are exactly the finite element shape function, with the only difference that you're not evaluating them or the Gauss points. So you don't know a priori where to evaluate your shape function, but you have to evaluate at each time step on the position of the material points that you found. But the rest is exactly the same as finite elements. And this is fine. This formulation is absolutely very common in finite elements, MPM and whatever. But as you know, well, we could simulate the failure of a dam break. We could analyze the ratio, the effects of the ratio on the dam break of a granular column, considering different meshes and different aspect ratio of A over H. This is taken by a paper from Lube, who gave us some tabular information, and everything is fine, no problems at all. We are, well, of course, we are not speaking of boundary conditions, and we are not considering the frictional boundary, the frictional condition on the boundary, so this might cause some differences, but more or less the results were quite nice. The problem is that if we want to deal with, for example, the classical example of a rigid strip footing or any other nearly incompressible example, so if we reach the incompressible limits, then we have some problem. Then we have some volumetric locking problems. So, for example, this is a problem of a rigid blocks who is going down in this, well, this is a soil, is the problem of the rigid strip footing. And if we look at the results, well, this is really nice, but not for computational. But it doesn't have any meaning. I mean, we have some problems. Yeah, we have some problem because we are using a standard Galerkin displacement-based formulation. So just U is the primary variable of our formulation. And this formulation is known to fail when Poisson ratio is reaching the 0.5 value. So basically, when we have we are reaching the incompressibility constraint. This is a very well-known problem, not only in MPM, of course, but in FEM, and there are many solutions, also some of them also for nonlinear problems, some of them also for large deformation problems. Most of them solve this problem using higher order elements. This is not the way we wanted to go. We wanted to stay with low order elements, so linear elements. And, you know, if you were listening to the beginning of my presentation, I'm coming from the CFD. So for me, mixed formulations are quite natural. It's natural to split the sigma into its volumetric and deviatory component, because this is the natural way to treat the Navier-Stokes condition, the Navier-Stokes equation, in which the Navier-Stokes equation are written. So one solution, it was to write a mixed approach for the solid mechanic problems. Of course, in the literature here you have some of the possible approaches. You can find many, but let's go for the mix to see what the mixed formulation are. Basically, if you remember before, we are just seeing the static problem, but it's extensible to dynamics since it doesn't affect the fact that it's a mixed problem itself. We have the divergence of sigma equal to the external forces. In the case of the mixed formulation, and in our case we use UMP formulation, we are splitting, we are explicitly putting into the momentum equation the deviatoric part of the sigma plus the volumetric part of the sigma. And pressure is also appearing, of course, in the mass balance equation itself. That means that both U and P are primary variables. So we are using them, we are using both of them as a primary variable, and this allows us to overcome the lock-in problems. Of course, we still have a set of boundary conditions, and the difference is that now we don't have a unique equation, we have a system of equations. We have the momentum balance and the mass balance equation downstairs. As before, we need to linearize this problem and we need to discretize this problem, since up to now what is written here in the weak form statement is just the continuous problem in weak form. But as you see, now you have two variables, not only one. We have U and we have P. Of course, U can be multidimensional, but let's consider it as a unique variable. Then, if we write our systems Kx equal to minus the residual, so the left-hand side times x is equal to minus the residuals, in this case, we can see the system as a block matrix, as a system of block matrices, in which if we reach the incompressible limits, this red matrix here, M, is going to 0. This is the classical form of, let's say, the extension of a Stokes problem. Let's take the Stokes problem as the original problems, then can be extended to more complicated problem itself. Also, in this case, if we look at the gray one block, so the stiffness matrix, the tangent stiffness matrix, we also have the material and the geometric stiffness matrix as before. The only thing is that, of course, in this case, we have a different definition of sigma, since we are explicitly dividing the deviatoric and the pressure, the volumetric part. And then we have the additional matrices that are appearing because of this splitting, and which are related, which are those matrices related to pressure, which are explicitly put on another block of the global matrix itself. And as I said before, then there is the matrix in block 2,2, which is going to 0 if we reach the incompressible limits. We know that this mixed formulation is not stable, especially in the compressible limits. I mean, if this is zero, this is the classical form of what is called a saddle point problems. So basically what is, you cannot choose arbitrarily the spaces where UMP, where to choose UMP. But these two spaces should be somehow linked, and the spaces of velocity should be much more richer than the space of pressure in order to allow this problem to be stable and to have them a unique solution. This is known in the computational mechanics community as the IMP-SUP condition, or Leditzenskaya, Babutska, Brezzi, LBB conditions, which is exactly saying that, I mean, you cannot choose the two spaces arbitrarily, but they need to be somehow linked. I don't want to enter these aspects, but it's quite important. So we also need to add to our mixed formulation a stabilization term, which allows us to overcome this problem. Ilaria chose to use the polynomial pressure projection stabilization, which was proposed by Bochev in 2000. That's basically possible. Well, it's very effective in static problem, and it works really nice. It has some drawbacks in dynamics problems. That's the reason why we are currently working on a variational multiscale stabilization technique to be applied to MPM. We developed a master thesis very recently on how to write a stabilized version using orthogonal subgrid scale and algebraic subgrid scale to the MPM problem. But as you see, I mean, you need to complete basically your system of equation with which a consistent stabilization matrix and vector R. Once this is done, then you can solve basically all ranges of problems. For example, a typical example is the Cook's membrane. It is a beam, but not very slim, with a force on the free boundaries and constraint on the left boundaries. Here there is a comparison of the mixed formulation without stabilization and with stabilization. Apparently displacement is quite good, but if you go to pressure, you see how pressure oscillates in the case of UP stabilization, while using the mixed stabilized formulation, it does not. And if you look at the comparison of the results in function of the number of elements, you look at the vertical displacement of the free tip of the membrane, you can see how the stabilized mixed formulation reached the solution much faster than, therefore, than the non-stabilized formulation, which shows some problem when we are reaching the incompressible case. But for sure, indeed, this UP stabilized formulation gives you an accurate solution, while the U solution gives a completely wrong solution in the case of the quasi-incompressible limits. So we need some sort of different approach, as mixed formulation, for example, for dealing with incompressible material or overcoming the locking phenomenon. This is another example, very simple one, of a plate which is under tension, and you see how the U formulation in the compressible case give wrong results, but not absurd results, while the UP formulation works fine in the compressible case. But if we go to incompressible case, then you see how the U formulation completely fails, while the UP formulation continues to work well. Okay, well, that's the same results. If we go back to the original rigid strip footing example we saw before, we can see now the comparison between the U formulation and UP formulation, which is much more similar to reality. Already here you see some diffusion. There are inconsistent results. The same can be seen on the vertical displacement. And of course, when you speak of the Cauchy stress as well. Well, here you see the same results, but just looking at the force. Well, just a video of what's the registry put in example. Of course, unfortunately, these results are element based, so it's not really nice to be seen. It's not as smooth as it can be if it was correctly post-processed, but it's not a real problem of calculation. Another aspects I would like to mention before starting speaking of a couple problem is boundary condition in MPM. Because I would say that most of people working in MPM and saying that MPM is the best technique ever says that one of the strong points is that boundary conditions are as easy and accurate as in FEM. And I agree with that sentence, but only in certain occasion. I mean, it is true as long as your boundary coincides, matches with the background grid. So if you can impose your boundary conditions on the nodes of the mesh, then everything is fine and it's good, as in FEM, because you already have the conditions on the nodes. But in many occasions you cannot, and then you have problems. Well, in this case, this is a sort of small silos from which sugar is coming out. This is sugar, dry sugar. And of course, you can easily build a mesh following the boundary of this axisymmetric geometry. No problems at all. And well, you can simulate everything. You can impose Dirichlet conditions, even moving boundaries in some sense. And of course, you don't have any problem with the Kronecker delta. So you know that the shape function of a certain node I evaluated on the nodes is exactly 0 if if I and j are not the same, and it's exactly 1 if I and j coincides, if I is equal to j. That means that you are exactly imposing your Dirichlet conditions on the nodes. The problem is that in many cases, if you have surface boundary condition, not volumetric one, in which case it's easier, or if you have moving boundaries, then things are getting much more complicated, because often you don't have a mesh on which to impose your boundary condition. Or, for example, consider this undeformed beam at the beginning, and consider this as a very, very flexible beam. Then it will be subjected to large deformations. And if you are imposing a force here, well, this force should follow your material points on the boundary, while the mesh behind will stay on its original position. So something like this will happen. How can you do that if you're imposing your boundary condition on the nodes? Well, you cannot impose them on the nodes. You have to find some way of imposing your boundary condition on the material points, and then to get it to the nodes with the less error possible. Well, there are many possible solutions. This is a very common problem not SPH, in MPM. So one possibility, which was published and explored by my colleagues here in Padova, by Francesca Ceccato, whatever, it's to move, for example, the mesh according to the material movement. This is possible in some cases, but also not in many cases. I mean, you need to be sure that deformation is not really affecting your process. So this is a good solution if you can, if your problems allows you to do that. Or you need to move the mesh according to the material deformation, but then you're deforming the mesh. You're going back to the need of remeshing, which is what you didn't want at the beginning. You're going back to FEM, basically. You don't want to remesh, but it might be needed. You can either use some other techniques for like ALI, arbitrary Lagrange Eulerian, or whatever, to move the mesh according to a given law. But this is not really in the direction of MPM. You can also use boundary particles. These boundary particles can be either the outer layer of your material particles, or can be an additional layer of outer particles without massless. Usually, it depends, but usually this is somehow the approach we choose, but with something more. Usually the problem is that you are then applying this condition on a band, not really on the surface. So you're somehow diffusing a little bit the condition you're imposing. Or there are high order solutions. So you can use B-spline, the group of Professor Kuhn use B-spline interpolation in the implicit boundary method to consider the boundary. That's a very interesting approach. I don't think it's still available for large deformation, if I don't remember. I mean, it's proposed for small deformation. Alternatives are the classical alternatives of finite elements, penalty methods, Lagrange multipliers, which have, well, the main drawbacks of Lagrange multipliers is that you're adding degrees of freedom and you don't want to change the structure of your matrix. Penalty method is indeed the simplest method, very precise, very effective. It has the problem that it can Hill condition the matrix you're solving. We decided to go for penalty method using boundary particles, so to minimize the diffusion of the information that we want to pass from the particles to the nodes, and the other way around. Because this problem of unfitted method is very common in coupled problems. In fact, in coupled problems, the boundary, the interface between the two materials that you're considering is moving and deforming according to your problems. So coupled problems in MPM. Well, basically we are just making a short overview of two different ways of two different approaches. One is the MPM monolithic coupling. So let's build one single system of equation. And the other is the possibility to couple MPM with other techniques. FEM is the natural choice for the reason we have already seen many times. It's MPM is just an extension of FEM, but it's not the only possible choice. So this is a tricky definition, MPM monolithic coupling. Actually, one of the strengths of MPM is that it can deal automatically with multi-materials. Since we are defining the properties of the material points, we can definitely use automatically different materials inside the same simulation. In this, what do I mean? Well, let's look at this image here in the slide. We can consider a structure which is the orange one, and the soil which is the green one. Okay. Initially, then you will have all the structure material points concentrated here, and the green material points in the lower part. But once and once you build up the systems, automatically the nodes that only have orange material points will just have contribution from the structural parts. The nodes that are parts of elements which only have green material points will be definitely only influenced by the soil parts. But then there will be these yellow nodes. These yellow nodes are nodes of elements in which both materials are present. This means that these material points, if you remember the original definition of material points, we are going material points by material points for the calculation of the local contribution to the nodes. These yellow material points I'm pointing with the arrows will give contribution only to these 4 nodes and will give his own contribution as structural material point, while this material point will give his contribution to the same 4 nodes, but as soil material points. Of course, they will give their contribution in function of their position, of their mass, and of their variable, of their internal variables. This means that these yellow nodes will have part of the stiffness contribution of one material, part of the other. In other words, if we translate this information into our algebraic systems and we divide all the nodes that just have the soil information, all the nodes that just have the structure information, and all the, let's call them boundary nodes, interface nodes, so all the yellow nodes, we see that the matrix will have some interface conditions where both materials are present, and other ways we'll only have the structure and the soil condition. What do I mean is that we are not coupling anything. This is naturally done in the assembling procedure of the MPM. This system is automatically built once we define different materials. And that's one of the strong points which is not present in finite element. Of course, we are basically only dealing with normal contact and sticky contact in this case. What do I mean? We are not considering any friction presence between the materials. This is not present implicitly. It can be added. People are working on that, but in the natural MPM, it's not present. Or it's a continuum. Remember, it's a continuum-based formulation, so these yellow and green bodies cannot separate easily. So neither in the frictional way, neither in the normal way. But the normal contact is well considered. So it's a sort of tricky way of saying that we are doing coupling, monolithic coupling, because actually we are just solving the MPM solve. But we want to go a little bit further. Why don't coupling MPM with other techniques? And why do we need this? Well, actually for many reasons. I will come back to this slide later. MPM is less accurate than FEM. We need MPM, we need particle methods in general because we are not able to do it to simulate large deformation with FEM. But if it's possible to use FEM, why don't use it? And in many cases, there are many kind of element technology which is not present in MPM, membrane shells, and a lot of structures that also 1D structures, cables, beam, truss, that are not present that are not easy to be simulated with MPM. Why don't we use directly the FEM codes? Not to say that all the work done on optimization, on topology and shape optimization is present in FEM. So why don't we exploit the maximum, the potential of FEM where it's possible and combine it with MPM where it's not possible? Typically, we can simulate large deformation of soil using MPM, but maybe the structure can be simulated using FEM itself. Of course, when we are speaking of combining different techniques in a coupled system, it's quite complicated to think to achieve a monolithic coupling. A monolithic coupling, it means that we are solving a unique system of equation all at once in a big system. That's complicated if you're dealing with different time integration schemes, if you're dealing with different element technologies, if you're dealing with different variables. And especially nowadays in which we are not reinventing the wheel every time, but maybe we're using codes that are already available in the literature, which are already well established and proved to work. It's not always easy to be so intrusive in the code, so to construct a monolithic approach. I'm not saying it's impossible, but it might be very difficult. The simplest approach is to use a staggered approach, which is let's use more or less the solver's MPM, FEM, or whatever technique you want as a black box. And let's interchange information between the two simulations. So which are the common staggered way of coupling information? Well, one-way coupling is the simplest one and quite useful in many engineering problems, by the way. We have two solvers, two different solvers, and only one is passing information on the other one. The deformation or I mean the solution of the second system is not affecting directly the first one, but it's affected by the first one. So it's only in one way decoupling. There is nothing coming back from the second system to the first one. While there are the second alternative is two-way coupling, and we can divide it into two main family of coupling strategy. The first case, system one is giving an input at every time step to system two. System two uses this input as a boundary condition, basically, and evaluates its new time step and gives a new variable to the system one as input for the next simulation. This is the so-called weak coupling because we are not reaching convergence in this loop. We are not looking for equilibrium between these two formulations, but we are just saying that the first is influencing the second is influencing the first, and we go further. While if we want to do it as accurate as possible, we are also iterating between these two coupling that I've just shown in the weak coupling scenario. That means in the same time step, we are going back and forth from system one to system two until we reach the convergence. So until we are doing we have defined exactly which is the influence that the first system is making on the second and the second is making on the first at the same time. Okay. Of course, this is physically possibly more correct conceptually, but it's not really always feasible. It's extremely costly, as you can imagine. So we need to evaluate what we are looking for, which level of detail we are looking for, how does it cost, and which are the instruments that we can use in that case. So there is not a unique answer on what it's better to do. Of course, I mean, the ideal would be to be able to do the strong coupling every time, everywhere, but it's not always possible. And maybe not useful from the engineering point of view in some cases, so should be evaluated. In our case, we try to do the strong coupling, but thinking of MPM and FEM, we have an additional problem, which is the non-matching discretization. If you're thinking of a structure discretizing FEM, this doesn't mean that the structure has a grid which is matching with our background grid, especially if the deformation of the structure is finite. So we have a problem also of passing information from two non-matching grid, which is an additional problem to be considered. I mean, it's not the same if we consider a structure in a finite element fashion, so let's say in a grid conforming fashion, in which we have clear boundaries on which we have nodes where we can impose either Dirichlet or Neumann boundary conditions, forces or constraint, or if we are considering a body, an MPM body, on top of a grid, which is not the finite element grid that we are using in the MPM code. Let's look at it in more details. Let's imagine we have a structure, the yellow one, the orange one. This is the real structure, which is discretized with this piecewise linear sequence of segments and nodes. This piecewise linear discretization of the structure should be seen by the MPM code here above, the green one, and substituted as a layer of boundary particles, which are those particles acting as coupling between the structure itself and our MPM code. And then this information catched by the boundary particles should be passed to the nodes of the MPM background grid, adding the contribution of the forces that the structure is passing. Of course, here in the middle between the orange and the green curves, there should be a mapper. In our case, we are using the mapper present in the Kratos multiphysics tool, which is for us a sort of black box. And as I said before, when I mentioned the no matching boundary condition, what we are using are boundary particles with penalty conditions. That means we are constructing a layer of an outer layer of massless boundary particles that are mimic the boundary layers of the structure itself. And well, the concept of penalty, I guess you all know it from your basic continuum mechanics courses. You are considering the presence of fictitious springs that are connected your boundary particle, in this case, to the nodes of the elements. And the higher the stiffness of the spring, the higher the penalty factor you're using, the stiffer the spring you are considering. And this is a way of imposing boundary conditions. This was one of the most common ways of imposing boundary condition in FEM as well. Very famous because it's not changing the degrees of freedom of your system. It's just adding a very high value in your stiffness matrix and in your right-hand side vector, so that you can somehow delete the Dirichlet conditions. So the reaction forces arriving on the nodes are given by the surrounding particle motions, of course, and by the penalty imposition, so by what it's arriving from the structure itself. And then we added also an evaluation of a possible contact condition using a gap function between the structure and the MPM node itself. Just very briefly, because this is well, this is the first application of penalty to MPM, but it's quite similar to FEM. So we define the weak form of the penalty imposition. So U is the constrained displacement, UB is the displacement of the boundary particles. We define it in a weak sense, and we arrive to the discrete form. That is translated into the general global system of equation in an addition of a matrix of a penalty inside the stiffness matrix and the right-hand side vector. This allows us to impose Dirichlet boundary condition. That is a boundary condition on the primary variable directly. So we are able to do examples like this, in which we have, well, in this case, a granular material and a linear and an elastic body and elastic beam. And also to reproduce examples that, well, this is not, of course, a fluid soil structure interactions example, but you will see in the next slide that, first of all, we use this example as a validation of our code, comparing our results with the experimental results and the numerical results obtained by Professor Bui with SPH. And more or less, we were in the same line of results, considering that we are not really dealing with the frictional boundaries, and we are not using any localization technique. So we are not able at the current times to simulate the fracture itself, or we are quite happy with the results we are obtaining. But then we use this example also to validate the possibility of considering the boundary as non-matching boundaries. So we didn't put nodes on the boundary of the slope, and we compare the results in the case of the conforming and unconforming case. So we repeat the experiments, but in this case, this boundary is not fitting with the background grid. And well, we obtained quite good results because the black line and the blue line, I don't know if you're able to see them, but are really matching. And considering the high nonlinearity, I think that this variation can be ignored, basically. And in this case, the penalty factor was around 10 to the power of 11. Using penalty techniques is easy, as I said before. The difficult part is that you have to calibrate the penalty factor, because if it's too large, you're hill conditioning your matrix, and this can compromise absolutely the calculation. So it's really problem dependent. That's the main drawback of this technique. Very well known, by the way, but it should be considered. We also repeat these other experiments, which we have 3 layers of soil constrained above and with roller supports on the side. Well, with the 3 different materials. Here you can find all the details of the materials. In this case, we didn't want to perform the failure analysis, but we use the shear strength reduction methods. Basically, we are increasing at any simulation the value of the shear reduction factor. That means that at every simulation, by increasing this factor, we are decreasing the cohesion of the material and the internal friction angle, until reaching at a configuration of these 2 parameters that cause the failure of the material itself. And the failure is observed when the maximum displacement is not reaching any stationary point, while in the first case as well, the shear reduction factor is 1.5 and 1.6, we achieve a maximum displacement, which is asymptotic. In the case of shear reduction factor 1.7, this is not achieved and it's not converging. And this is it's analogous to what obtained by the literature review. Then a classical failure analysis of a slope made by 3. What can we see? What can we analyze on the dynamics of this failure? Well, if we compare our results with FEM, we are in line with what it was obtained by FEM. We are obtaining the same bishop circle. FEM cannot deal with large mesh distortion, so it's even more rigid than we are. We do not have any localization techniques, so we cannot obtain what is obtained here in SPH, so the discontinuous failure. In our case, it's just a continuous deformation that we can observe. And we are using no-slip contact condition that can cause much higher mass mobilized at the toe of the dam than in other cases. But let's say that, I mean, we are in line with what is presented by the other technique with FEM and SPH. Yeah. Another example of, in this case, a dam break example impacting on a beam, this wall. This wall is either, in one case, a rigid wall, concrete-like, or a rubber-like wall, very flexible. Okay. In the case of the concrete wall, you cannot observe any deformation, but in the case of the rubber one, you can. What can we observe? Well, also in this case, we consider the case of conforming and non-conforming boundaries, and both the monolithic and staggered coupling strategies presented before. So we consider also the wall And we discretize and use MPM also for the wall, the orange wall, not only for the soil. And then we consider a FEM wall with an MPM soil. What can we observe? Well, if we look at the final results of these two different strategies for two different meshes, the more fine meshes below, on the right, we have the MPM-FEM staggered coupling. On the left, the monolithic coupling. Well, we can see, looking at the monolithic coupling, in the case of the concrete wall, well, you observe that, yes, you see oscillation, but basically we are around zero as value of oscillation, because it's the vibrating of the wall which is causing vibration of the wall due to impact, which is causing this oscillation. We have a progressive refinement of the mesh to converge to a solution. And in the case of a rubber-like, yes, we see that we are also converging to a solution while refining the mesh. The interesting part is to compare the monolithic and the staggered approach, because if you remember, in the monolithic case, so in the MPM analysis, basically we have a sticky contact. So we are we are not considering any frictional contact, and everything is more rigid than in the staggered part. In fact, you see that the monolithic approach achieve a lower peak than of deformation peak, displacement peak on the wall than in the case of the staggered one. And it's more rigid in general. The vibration, the period is much more short. The frequencies is higher than in the staggered case, as expected, by the way. So we need to consider these differences when dealing with a real problem. And then the failure of a slope, homogeneous in this case, with and without this retaining wall. Well, this simulation is without this retaining wall and was compared with the SPH solution obtained by Professor Bui. Yeah, with similar results. Also, yeah, they are, also in our case, we are considered unfitting, non-matching meshes. And we did a qualitative test, but we need to go further and and analyze it more in details with a 3D example. In this case, the wall is a flexible one. Sorry, I interrupt the video. And you see that the presence of the wall is decelerating the slope while failure occurs, but it's a rubber-like wall, so it's really, really highly flexible, and it's not blocking anything. But it's just a qualitative test. We need to go much further with that. And this is the deformation of the wall, of course, for a factor of 2050, because the deformation is really few. 3 point of analysis on the tip of the wall, but you can see the different oscillations. That's almost all. As you see, I've done an overview, not as exciting as the previous talk, but on the basics of MPM. I hope it was useful. And the basic message is very much in line with what Professor Bui said in the first lecture. If you can use FEM, definitely. But there are many situations in which you can't use it. And particle techniques are really necessary. They are not completely well accepted by many communities. One of these communities is the mathematicians. They still look at the particle techniques as something which is not under control, because there are, in the case of MPM, for example, there are very few convergence analyses, and the convergence rate is not as good as in FEM. You're paying a price for having this capability, and well, we need to go much further and study and continues in this line. We need a common framework for all the particle-based technique, which is still missing, and it was also commented by a previous colleague. And unfortunately, we are still at the research level. I mean, very few engineers, practitioners are using particle methods. But I mean, slowly, we are increasing our popularity. Just, I will leave you, well, you will have this, the PDF of this talk, so you will have all the references, some papers. The PhD thesis of Ilaria, if you want, is available, and the master thesis of Nanda and Gloria are also a good lecture if you want. And just to conclude, all you have seen today was developed inside Kratos Multiphysics, which is not only an MPM code. Absolutely, it's a multiphasic code born more than 15 years ago already for multiphysics in finite elements. And slowly, it was also converted to a multi-technique framework because times have changed, and you can find DEM application inside Kratos. You can find our particle-based application on MPM. You can find PFEM inside Kratos. So it's not only finite elements, it's much more than this. It's a monster, it's very huge. It's a multi-physics big platform. The community is increasing every time. It's open source, you can download it, and it's written in C++ with an interface in Python for using the application. And all of us provide an interface with GAD. So it's not the only pre and post process you can use, but it's the default one for which you will find interface. By the way, there is an interface you can directly download in the GAD website of the Kratos that you can use without installing the code for developers. You can just download it for users and use it, and you can use our MPM application here inside. Happy to help if you need. Which is the philosophy of Kratos? Well, Kratos is a collection of libraries, and it has a core in which all the common features are inside. So solvers, data structures, spatial containers, all the things that should be repeated in any application and are commons to any application are there, and you can use them. And you can put the physics of your problems inside what is called application. That will be connected to the core and as its peculiarity features inside. All the applications are built with a common structure and with a common language so that they can be easily coupled. You will find the fluid structure application is one of the most common couple application, the thermomechanic application, our particle mechanic application, which is also a couple. I mean, it's an application derived by the structural mechanic application, in part because there are many features of the FEM codes that we can use. And this is done to, well, improve the reusability of what is developed there and to reduce the conflicts between different physics. Nothing more. I mean, thank you again for the audience for listening to this talk, and hope you enjoy it. And if you have any questions, I'm happy to answer.